Welcome back to Algebra. Today we're going to get ourselves started on chapter 12. And what this chapter deals with is a mathematical pair of ideas called sequences and series. And we're going to today define both of these and give you guys some simple examples of each of them. All right, so we'll start off with our definition for a sequence. By definition, a sequence is a function or equation whose domain are consecutive integers. Now, remember when we use the word domain, those are the numbers that are allowed to go in to an equation or into a function. But with sequences, we usually start, let me highlight this for everybody. We usually start sequences by inputting the number 1. It can actually be any number, but traditionally we start with the number 1. So a sequence is a function or equation whose domain are consecutive integers. All right, so that means, again, let me highlight this in red. Because the domain are going to be integers, we're not going to be inputting decimals or radicals or fractions. We're not going to be inputting anything into our equations other than integers. Okay, so some of the notation that we're going to use before we get to an example, and you just need to get used to both of these fellas. The notation that we're going to use for sequences and series are either functional notation, so we'll use our traditional letters like F, G, H, R, just about any letter is fine. But instead of having the independent variable be X, like it normally is, with sequences we almost always use ands. It can actually be other letters, but traditionally we use ands. So this would be called functional notation, which you guys have seen a lot over the course of the year. And then a brand new notation is this second one. Another way in which we can write sequences is to use one of the first few letters of the alphabet, so A's, B's, C's, and so on. And then as a subscript, remember super is above, sub is below. As a subscript, attach whatever variable we're talking about. And again, usually it's going to be n. So this is then called sequence notation. All right, so those are the two that we're able to use. And so the idea is we're going to be given a function or equation like f of n equals 2n plus 3. And then what I would ask you to do is find f of 1, f of 2, f of 3, f of 4, f of 5, so on. The idea is I'm asking you to find the values for the function when we input input consecutive integers like 1, 2, 3, 4, 5. And of course we could keep that going as long as you guys wanted to. Okay, so what would f of 1 be? Well, all that means is wherever you see an n, put in this value. So since I'm asking you for f of 1, this would be 2 times 1 plus 3. What's f of 2? Well, that's just simply going to be 2 times 2 plus 3. What's f of 3? And I think you guys will get the idea. Everywhere we see an n, we just continue to put in the next consecutive integer until we get to f of 5, which would be 2 times 5 plus 3. Now I'll ask you to do this arithmetic all of the time. So 2 times 1 plus 3 is 5. 2 times 2 plus 3 is 7. 2 times 3 plus 3 is 9. 2 times 4 plus 3 is 11. 2 times 5 plus 3 is 13. And traditionally, the numbers that come out, once we put in consecutive integers, whatever numbers come out are usually called terms. So we call these the terms of the sequence. The terms of the sequence. Okay, and so I'm just going to ask you to bop through a few examples. I'm going to give you a sequence, and then in these examples, what I'm going to ask you for, guys, is the first 5 terms of each of the sequences. So again, since we're talking about the first 5 terms, unless you're told otherwise, and there is going to be examples where you'll be told otherwise, but unless you're told otherwise, the first number you put in is 1. So we're going to put in 1 for n, then 2, 3, 4, and in all of these examples, I'm going to ask you to find the first 5 terms. So we're going to go from 1 through 5. So everywhere we see an n, we just simply put in 1, 2, 3, 4, and finally 5, and do the arithmetic. I don't care if you do it in your head or on your calculator. A lot of this is easy enough you could do it in your head, but your choice. So negative 3 times 1 plus 1 is negative 2. Negative 3 times 2 plus 1 is negative 5. And I'll just pop a few of these out. Negative 8, negative 11, and negative 14. So again, these results are called the terms of the sequence. Okay? The sequence is actually the equation itself, but what comes out are called the terms. Let me do a few more. The new notation here, instead of f of 1, f of 2, f of 3, and so on, now we're going to have a sub 1. Again, unless we're told otherwise, the first number that goes in is 1. So I'm going to find a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5. Again, the idea is everywhere I see an n, replace it with a 1, replace it with a 2, replace it with a 3, replace it with a 4, and finally replace it with a 5. Okay? Maybe some of the problems in your book will ask you for the first 4 terms. Well, you only have to go up through 4. If they ask you for the first 6 terms, you have to go up through 6, whatever it might happen to be. And again, doing the arithmetic, 1 squared is 1, times 4 is 4, minus 3 is 1. 2 squared is 4, 4 times 4 is 16, minus 3 is 13. And again, I'll just get a few of these going. 3 squared is 9, times 4 is 36, minus 3 is 33. 4 squared is 16, times 4 is 64, minus 3 is 63. And 5 squared is 25, times 4 is 100, minus 3 is 97. Okay? All right. A couple more, just changing up the types of sequences that it could possibly give you. This one's actually a titch easier. I just chose a different letter. Instead of f of n, I chose g of n. But again, asking you for the first 5 terms, you're just going to help me find g of 1, g of 2, g of 3, g of 4, and g of 5. Just replacing n with 1, 2, 3, 4, and 5. And then digging out your calculator or just doing these in your head. 1 to the third is 1, 2 to the third is 8, 3 to the third is 27, 4 to the third is 64, and 5 to the third is 125. Okay, and the last basic example here, first 5 terms for this number 4 example. Again, with the a sub n, instead of g of 1, g of 2, g of 3, we'll have a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5. Again, everywhere we see an n, replace it with a 1, replace it with a 2, replace it with a 3, with a 4, and with a 5. And again, just doing the arithmetic in the correct order, exponent first, addition second. 2 to the first is 2, plus 1 is 3. 2 squared is 4, plus 1 is 5. 2 to the third is 8, plus 1 is 9. 2 to the fourth is 16, plus 1 is 17. 2 to the fifth is 32, plus 1 is 33. Okay, so there's some examples of starting with a sequence and then giving me or finding the first 4, 5, 6, however many terms we might ask for in any sequence. Okay, now we can also ask you to do these problems in reverse, meaning we give you the terms. So in this example, I'm giving you the terms of a sequence, and then what I'm going to ask you for is the equation or the function. And if you're not told otherwise, it's totally up to you how you want to do it. As an example here, it doesn't say find f of n or find a sub n, so it's totally up to you how you want to do it. It doesn't matter. You could use either one of these. You don't have to do both, just one or the other. But give me an equation or a function that would give out 3, 5, 7, 9, 11. Okay? So how in the world are you supposed to find the equation? Well, the idea is, remember that unless we're told otherwise, we want to put in 1 for n and get out 3. Put in 2 for n and get out 5. Put in 3 for n and get out 7. Put in 4 for n and get out 9. Put in 5 for n and get out 11. And how can we do that? Can you think of an equation that would get you that? Well, there's going to be some tricks that help us with these. One is going to be to ask yourself, do these terms go up or down by the same amount every time? In this case, of course, the terms are going up. So do the terms go up by the same amount? 3 to 5, 5 to 7, 7 to 9, 9 to 11. Do they go up by the same amount? Sure. Here they're going up by 2z's, right? They're going up by the same amount. So that gives you kind of a hint, a clue. So that means that every time n changes from 1 to 2 to 3 to 4, the result is going up by 2's. But that doesn't quite get the job done because 2 times 1 is 2, it's not 3. 2 times 2 is not 5, it's only 4, and so on. So we have to make an adjustment, and what adjustment could we make? If we add 1 to the result. Now feel free to try it out for any of those. As an example, now try out 5. If you put 5 in for n, 2 times 5 plus 1, hey, that does get you 11. Okay? So these will be a little bit tougher. These will be a little bit tougher trying to find the sequence, the equation itself that gives out the terms. Let's try another one. Find the sequence. This time I won't give you both of them. I'll just give you one of them. So I'll just write this one as a sub n this time. But the idea is put in 1 for n and get out negative 4. Put in 2 and get out negative 8. Put in, that's a typo, put in 3 and get out negative 12. Put in 4 and get out negative 16. Can you think of how to do that? Again, do the terms go up or down by the same amount? Here they're going down by 4z's. All right, and so a nice simple equation that would work is to have the equation a sub n equals negative 4 times n. And if you give it a try, you see it works for all of the terms given. Okay, let's try another one that's going to be a little bit harder. All right. Just for a little variety, let's call this one f of n. Again, if it doesn't ask you specifically to write it one way or the other, it's just your choice. But the idea again, put in 1, 2, 3, 4, 5, and get out 2, 5, 10, 17, and 26. All right, can you think of something that works? Again, probably the easiest way to start is to ask yourself, do the terms go up by the same amount every time? Nope, not this time. This time they go up by 3, then they go up by 5, then they go up by 7, then they go up by 9. Gee whiz, that's not the same amount every single time, right? Do you recognize the numbers? In fact, let me use my deluxe eraser here just to get rid of those. Those are not going up by the same amount every time, so I'm just going to erase that to try and leave a little bit of room. Do you recognize the numbers at all? Are they familiar? 2, 5, 10, 17, 26? Probably not. All right, they probably seem pretty random. But if I rewrite all of them slightly, I think you'll see the pattern. I think everyone agrees that 2 could be thought of as 1 plus 1. 5 could be thought of as 4 plus 1. 10 could be thought of as 9 plus 1. 17 could be thought of as 16 plus 1. 26 could be thought of as 25 plus 1. Now, if I change colors here so I could highlight it, do you guys recognize a pattern in that first number? The 1, the 4, the 9, the 16, and the 25. Do you recognize a pattern there? 1, 4, 9, 16, 25. Those are all of the integers squared, right? 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. So our formula then can be the integer squared plus 1. And if you check it out with any of the terms, you find that that works. That works for all of them. So obviously a much more difficult one there. Okay, and let's finish off with one where the terms of the sequence are fractions. Now remember, all we said before was that the numbers that go in, the domain values, are going to be integers. It's okay to get out fractions for answers. But let's give this one a name. Let's call this one b sub n. Again, you can use any of the first few letters of the alphabet for names of sequences. Again, the idea, put in 1, 2, 3, 4 for n, and what we want to get out is 2/5, 4/6, 6/7, 8/8, and so on. Now, since all of the terms in my sequence are fractions, I'm going to start out my equation with the fraction line. And what I'm going to ask you to do is just think about the problem half at a time, meaning just take a look at the top of each of the fractions. All right, just look at 2, 4, 6, 8. Don't worry about the denominators right now. What can you do to 1 to make it a 2? 2 to get to 4, 3 to get to 6, 4 to get to 8. What can you do to each of our domain values to get to 2, 4, 6, 8? Well, that's pretty easy. We just simply multiply by 2. So the numerators are going to work out if we just set the formula up to be 2n. Okay, now we have to make the adjustment. Now look at the denominator, so let me switch colors. Now I need you to look at 5, 6, 7, 8. And what can we do to 1, 2, 3, 4 in our domain to get to 5, 6, 7, 8? Well, all we have to do is take the value for n and add, how much? Add 4. Okay, so one equation then that works would be 2n over n plus 4. Alrighty, so there's just some basic examples of some sequences. Now the second thing we're going to talk about in this chapter is what's called a series. And what happens with a series is we take the terms of a sequence, right? So we just looked at examples where we either were given the terms of a sequence or we had to find the terms of the sequence. And what we do with the series is add them together. So sum, of course, you guys, you know this one, sum means add. So when we have below 5, 8, 11, 14, 17 separated by commas, those are the terms of a sequence. But when I replace the commas with plus signs, now instead of just listing out the terms, now I'm adding the terms. Now it becomes a series. All right, so a sequence are the terms separated by commas. A series is the terms added together. Okay, and the notation that we use to indicate a series, we use the Greek letter sigma. All right, so this weird symbol, this crazy looking E that I just wrote down is the Greek letter, and in fact, to be more specific, it's the uppercase Greek letter sigma. Now you might remember the lowercase sigma from chapter 11. The lowercase sigma, remember that was the O with the little hat on it. That was our symbol that we use for standard deviation. Okay, but now what we're going to do is we're going to use the uppercase capital sigma, and it's kind of this crazy looking E. All right, but that's the symbol that we use in advanced mathematics to indicate a series. Indicate, anytime you see this in the rest of your math or science life, what you're going to be doing is adding things together. You're going to be adding things together. Okay? And so what's going to happen with our summation notation whenever we have that Greek letter sigma is we're going to have some number value here on the bottom of the sigma. That is our starting value. Then we'll have a number on the top. That's our last value. And then what we'll have right here is the equation or the formula for a sequence. So we start with a sequence. The sigma tells us to add. The number below tells us the starting value to begin with. And the number on the top is going to tell us the last number that we want to start with. Okay? All right, so I know it looks kind of crazy right now, but when you see some examples, you'll get the hang of it. So here's a couple of examples that we're going to walk ourselves through. All right, my number one example says find the summation from j equals 1 to 5. Now the bottom number means this is the first number that we're going to put into our series. The number on the top is going to be the last number that goes in our series. And what we have right here is the formula or the equation, whatever you want to think of it as. In fact, let's not use the word formula. Let's use the word equation instead, because we're more used to that. So that would be the equation. So wherever I see a j, what's the first number that goes in? 1. So I'm going to have 2 times 1 plus 3. But instead of using a comma, which we would have with sequences, now we're going to use a plus sign because the Greek letter sigma means add. Now what's the next integer after 1? Well, 2. So the next number we put in is 2. And we keep going until the last number that we put in is a 5. So I have to use a 3. I have to use a 4. And I have to use a 5. And now what I need you guys to do is the arithmetic. 2 times 1 plus 3 is 5. 2 times 2 plus 3 is 7. 2 times 3 plus 3 is 9. 2 times 4 plus 3 is 11. And 2 times 5 plus 3 is 13. And then dig out your calculators and add these together. So 5 plus 7 plus 9 plus 11 plus 13 is, let's see, 12, 21, 32, 42, 45, I think. If I did that okay in my head. All right? So what we're looking for now, the answer to a series or summation problem is just going to be a simple number like 45. Okay? Now the bottom number does not always have to start off at 1. Sometimes it can start off at something else, like in my second example where it starts off at 4. So the first number that's going to go in is 4, and the last number that's going to go in is 7. Now the equation here is 2 to the x. So all we have to do is start by putting in 4, add, because the sigma always means add. Then put in the next number, which would be a 5. Then add, put in the next number, which would be a 6. And you keep this going until you put in the last number, which is a 7. So the first number that goes in is 4, and the last number that goes in is 7. And again, I just need you to do the arithmetic, again, either in your head or on a calculator. 2 to the 4th is 16, 2 to the 5th is 32, 2 to the 6th is 64, 2 to the 7th is 128. And I'm going to use my calculator here so I don't get that messed up for anybody. 16 plus 32 plus 64 plus 128 is 240. So we say the summation is 240. Okay? All right, just continue to try a couple more examples. Here's 2 more. Here's the summation. The first number we want to put in is 3, and the last number we want to put in is 5. So we just simply use the equation, and everywhere you see a k, you start by putting in 3. So 3 times 3 squared minus 7. Plus, again, the sigma says add. Then the next number is a 4, so it'd be 3 times 4 squared minus 7. And then the last number we put in is on the top of the sigma, that's a 5. So it'd be 3 times 5 squared minus 7. And again, I just need you guys to do the arithmetic. 3 times 3 squared minus 7 is 20. 3 times 4 squared minus 7 is 41. And 3 times 5 squared minus 7, 25, 75, 68. Again, feel free to double check my arithmetic there. And then when I add, because the sigma always means add, 20 plus 41 plus 68 would be 129. If I did that okay, I got 129. All right? And we can have all kinds of different things. My last example, I'm going to ask you to start by putting in a 1 and then go up to a 6. Please be careful if you're taking notes on this one. Please notice the negative attached to the I. So we'll put in 1, but that'll then become 2 to the negative first. Put in 2, but that'll then become 2 to the negative second, and so on. So we keep putting in numbers until the last one we put in is 6. So the last term is going to be 2 to the negative 6th. And then I just need you guys to do the math. 2 to the negative first is a half, 2 to the negative second is a fourth, and so on. Out to the last one, which would be 1/64. And then I'm just going to need my calculator to punch out the math on this one, guys. So just give me a second here. 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus, what's the last one there? 1/64. And let's see what we come out with, 63 64ths. Okay? Alrighty. And then just to finish off, I know this one's going long, but we're almost done. How much fun would one like this be? All right, if I ask you guys to have some fun with this summation. Summation from I equals 1 to 300 of I squared. Well, the first number that we're supposed to put in is a 1, and the last number we're supposed to put in is a 300. So this would mean everywhere you see an I, put in 1, then put in 2, then put in 3, and keep that going until the second to last number you'd put in is 299, and then the last number would be 300, right? How tough would that be? Oh, it'd be a huge use of time. You'd be using all kinds of time to punch out 300 squared numbers. So on certain problems we need some shortcuts, and so therefore we have some formulas, okay? So you might need to pause the video so that you can get these written down into your notebooks, but you're going to need a couple of formulas that will help you in certain situations, okay? And so feel free to pause and make sure you write these down and box them in somewhere. The first one says that the summation from I equals 1 to n of c. Now in this case, in this first example, c represents a constant. So c is going to be a number like 4, or 11, or -8. C is just going to be a number. And so when we have that situation, what that's going to be equal to is just whatever the heck the constant is, multiplied by n, where n is the upper limit of summation, the top value. Okay? Then another formula is if we have the summation from I equals 1 to n of I, right? What we can do is just simply take the top number times the top number plus 1 and divide by 2. And finally, if we have a situation where we have I equals 1 to n of I squared, what we can do is just simply take the top number and multiply that by the top number plus 1 times 2 times the top number plus 1 divided by 6. Okay? Now just to give you a heads up, for right now you're just going to have to trust me that these three formulas are correct. But in pre-calc, when you guys come back as juniors, I'll actually prove all of these formulas to you. Right now, if you wanted to check any of them, feel free by writing out all of the terms. But you'll see that all of them are true. And I'll prove all of these and quite a few more when we get to pre-calculus. Okay? Now what that's going to allow you to do then is our problem where I asked you guys to have a little bit of fun and find the summation from I equals 1 to 300 of I squared. Again, what this actually would be, you don't want to do all of the work, but then again, this one would actually be 1 squared plus 2 squared plus 3 squared and so on, all the way out to 300 squared. All right? But notice that this fits the formula because our formula is just a variable squared. All right, so that's our shortcut number 3, a variable squared. And so what the shortcut says is, take the top number, multiply by the top number plus 1, so 300 plus 1 is 301. Multiply that by 2 times the top number plus 1. 2 times 300 is 600, plus 1 is 601, and then divide by 6. And when I use my calculator to punch that out for everybody, 300 times 301 times 601 divided by 6 would get us 9,045,050. And that would be the sum of those first 300 integers squared. And again, if you don't trust me, go ahead and write out all 300 and add them together. Okay? But we can use the shortcuts for lots of other ones, like my second example here. The summation from I equals 1 to 150 of I plus 5. Notice the I is just a single variable, so we're going to use shortcut number 2. And then the second term is just a plain old number, so there we're going to use shortcut number 1. So this is essentially just going to be the same as the summation from I equals 1 to 150 of I plus the summation from I equals 1 to 150 of 5. Okay, so here, single variable, so our shortcut says take the top number times the top number plus 1 and divide by 2. And then the shortcut for just a plain old constant is going to be the constant times the top number on the sigma, on the summation. And I'm a little short on room, but I'll punch these out for you guys. 150 times 151 divided by 2 is 11,325. 5 times 150 is 750. And I've got to go off to the side to write my answer then. So when I add those two folks together, I should get 12,075. All right, and I've got one last example and then we'll call it a day. The summation from I equals 1 to 80 of I squared plus 4I minus 7. Again, you don't want to use up all of your day putting in 80 numbers into a formula and then writing out all 80 of those terms. It would take you too long. So if we use our shortcut and just think of this as the summation from I equals 1 to 80 of the first term plus 4 times the summation from I equals 1 to 80 of I minus the summation from I equals 1 to 80 of 7. So please notice what I did. I just wrote down the I squared. Here I split the 4 and the I, and then here I have my 7. And I've set this up now if I change colors so you can see it. Now what I've got is a formula with a variable squared, a variable to the first power, and a constant. So we can just use each of our shortcuts for this. The formula for a variable squared, we take the top number on the summation times the top number plus 1 times 2 times the top number plus 1 divided by 6. For a variable raised to the first power, we take the top number times the top number plus 1 divided by 2. And for a constant, we take the constant and multiply by the top number. All right, feel free, take a look at each of the shortcuts and see how they match up to what I just jotted down. And then it's just a calculator problem. 80 times 81 times 161 divided by 6. Oops, sorry about that, doggone. I hit the wrong button there. Let me do that again. 80 times 81 times 161 divided by 6. There we go. Is 173,880. 4 times 80 times 81 divided by 2 is 12,960. And 7 times 80 is 560. So when we add and subtract those three numbers, 173,880 plus 12,960, 12,960, yeah, minus 560. What we'd get as a result then is 186,280. Okay, a lot more economical, a much better use of your time. Instead of writing out, using that equation 80 times, putting in 1, then 2, then 3, then 4, then 5, then 6, then 7, all the way up to 80, we can get it done using our shortcuts. Okay, so we're all done with section 1, so feel free to stop this video and then go ahead and try the assignment for 12.1. Send me an email or give me a call if you have questions on any of the problems. Hope you're having a good day. Talk to you soon. Bye.